When last we met, I introduced the idea of acceleration, the rate of change of velocity. One of the ways that I described that was in the context of the unit, meters per second per second. Acceleration describes when the velocity changes by a certain number of meters per second every second. And I'd like to investigate that idea in the context of a very specific acceleration. It turns out that when things move under the influence of gravity, they accelerate with a very particular acceleration. I know right off the bat that it's accelerated motion because if I take my marker, for example, and I throw it upward, as the marker rises, it slows down. Its velocity decreases. Everyone knows that that's caused by gravity. As the marker falls again to my hand, it speeds up as it goes, going faster and faster in each second. And everyone knows that's caused by gravity. What you may not know is that the acceleration that gravity causes is constant, as long as we stay near the surface of the Earth. The acceleration due to gravity, which I'm going to call A, gets its very own symbol. It's so special, and we love it so dearly in our physics, that we're going to use the symbol G for the acceleration due to gravity. Makes sense? G for gravity. When we do experiments near the surface of the Earth, we find that an object that is going upward or downward makes no difference, moves with an acceleration of 9.8 meters per second squared. That means that gravity adds or subtracts 9.8 meters per second in every second. Today, for the very first time, we're going to be doing some calculations using our favorite physics equations of the moment. So to ease that along, I'm going to say that 9.8 is approximately equal to 10 meters per second squared for this whole discussion. It'll make it easier for me to do the calculations so that I can focus on the physics ideas without worrying about any of the math, even though I am going to use equations. Motion solely under the influence of gravity is called free fall. The best explanation I can give to you for why that's a good name is that I'm only considering the influence of gravity. An object is falling freely, and I'm not considering any air drag force that might be acting on the object as it falls. When a skydiver jumps out of an airplane, for example, as they begin to fall, they accelerate, going faster and faster. But eventually, they reach a point where the influence of gravity downward is exactly equal to the air drag upward, and they start falling at constant speed. Good thing, too, because if we treat the falling as free fall, gravity only, gravity adds 10 meters per second to the velocity for every second that you fall. It makes it very easy then to figure out what your velocity will be after a certain number of seconds, because our equation for velocity is simply the acceleration multiplied by the time. So here I have a cliff drawn and a rock or something has been dropped from the cliff and falls, and I see it pictured again here at 3 instances, at 1 second, 2 seconds, and 3 seconds after it's released. The math here is spectacularly easy, but I want you to think about the context of the meaning of acceleration. Gravity causes an acceleration of 10 meters per second squared. That means that gravity will add 10 meters per second for every second that this object falls. To me, it then becomes completely obvious. If I look here after the object has fallen for 1 second, I know that it'll be traveling at 10 meters per second at this point, because as it falls in 1 second, gravity will add 10. In the next second, gravity will add 10 again. So it's 10 meters per second, 20 meters per second. And then in the next second, add 10 again, 30 meters per second. I think that's a pretty obvious description of what happens. It also matches my everyday experience in that when a thing falls, it goes faster and faster as it falls. which I can see here on this motion diagram because the distance that it travels in the first second is a bit smaller than the distance that it travels in the second second, is smaller again than the distance it travels in the third second. And the reason why, of course, is that in every second it's going faster and faster and faster. And as you travel faster, you travel farther in each second. So this diagram makes sense, and gravity is adding 10 meters per second in every second. Well, I'm going to consider another motion here that pretty much encompasses everything that I want to describe about free fall motion. I've drawn here a building that I claim is about 25 meters high. Just as I'm using 10 for the acceleration due to gravity to ease my way, I'm not going to worry about the exactness of that 25 meters. From the ground to this little stick figure character's hand is about 25 meters. The stick figure, by the way, has a name. Throughout our time together, we're likely to encounter these stick figures because I personally draw them all the time. This particular stick figure is named Slim, a very apt name for a stick figure. He has a wife named Peg, and together they have a son named Twig. Twig has a pet horse named Matchstick. Twig also has a cousin named Rod. All of these characters will make an appearance at one time or another. But here's Twig, not Twig. This is Slim. Slim is standing on the roof of a building, and he's going to throw a ball upward with a velocity of 20 meters per second. You can see I drew it on the diagram here. Now, I can describe this motion qualitatively in a way that everyone here understands without ever having taken a physics class before. He throws the ball upward, and as it rises, it slows down until it stops at the highest point in the motion. It's possible that we never really thought about it as when it reaches the highest point, its velocity becomes zero for an instant in time, because that's on the verge of quantitative. But I think we all appreciate when it reaches the highest point, it turns around and falls again. And as it falls from this highest point, it falls going faster and faster and faster as it falls. Now, I'm going to imagine here that Slim doesn't catch it and it doesn't hit the side of the roof. It just continues on until it hits the street below. This is the problem that I would like to solve. Now, in my physics so far, I have two equations that I can use. I'm going to break out the first equation that predicts the velocity in the future, one of my favorites. V is equal to V naught plus AT. And when I read it, the final velocity is equal to the initial velocity plus the acceleration times time. The reason why I brought this equation out is because I want to see what I can figure out with it. I'm interested in the motion from the instant the ball leaves Slim's hand to the instant that it reaches the highest point in its motion. That's the motion I'm describing, and I would like to see what this equation has to say about it. Now, ordinarily, this equation is used to find the final velocity, but I would argue I already know the final velocity. When I throw a thing upward, it slows down and slows down and slows down until it reaches the highest point where it stops. So I already know that the final velocity is equal to zero, which is why I've inserted it here, replacing the v in my equation with what I know the final velocity be equal to, 0. The initial velocity was just told to me. I'm told it's 20 meters per second. Maybe this was written as a problem statement. Slim stands on a roof and he throws a ball with a velocity of blah, blah, blah. And I read from the words, but it's told explicitly that it's 20 meters per second. The 20 meters per second is explicit information, and the 0 meters per second is implicit. I use a little bit of my reasoning and my understanding about nature in everyday life to imagine that, yes, it does stop at the highest point in the motion. A physics problem doesn't always tell you that. Part of being a physics student and skilled at it is realizing these little things about nature. It stops at the highest point. For the acceleration, I'm putting in -10. Hang on a second. What do you mean -10? Well, if I think back to the definition of acceleration, I appreciate that positive acceleration means that I add 10 meters per second in every second. And negative acceleration would mean that I subtract meters per second in every second. Solving physics problems isn't just about plugging the right numbers in the right places. You have to think about it. It's very appropriate here for me to write the acceleration as -10 because I've chosen upward to be the positive direction. I can actually signify that on my diagram by making a little addition here. I'll say that this is where my number line's 0 is, right where he releases it when it's on its way up, and I'll choose that as the positive direction. I draw this little icon here with a 0 and upward the positive direction to indicate that I've chosen my number line to be like this. I don't have to draw the whole number line. That would be overkill. It's pretty clear that if I chose upward to be the positive direction here, that downward is the negative direction. So that 20 meters per second upward is a positive velocity. And I know by the nature of the thing that as it goes up, it's going to slow down. Everyone knows that that's true. Well, in order for the velocity to decrease, I'm going to have to subtract velocity away in every second. That's why the acceleration's negative. Negative acceleration means subtract velocity away, which is what has to happen for it to slow down as it rises. Now, you might be thinking to yourself, appropriately so, I don't need no equation. If it's going at 20 meters per second and I subtract 10 every second, it's going to take 2 seconds before I run out of velocity. That's absolutely right. But of course, I've chosen easy numbers here. I've chosen easy numbers. If it were decimals, you might prefer to the equation. And in fact, you see that the equation tells me exactly what I expect. The final velocity equal to 0, the initial velocity 20 minus 10 times t. I do a little bit of algebra to rearrange it, and I discover that t is indeed equal to 2 seconds. The quantitative assessment of the equation matches the qualitative description that I understand from my appreciation of the way nature works. So I used one of my equations to get one answer. My other equation is an equation that predicts the position in the future. Well, I like that because a question that I might very well have here is, how high does it go? I might want to know, how far up is that? And in order to figure that out, I'm going to break out my other equation of motion that I also love dearly, the one that predicts the position in the future. X is equal to x naught plus v0t plus 1/2 the acceleration multiplied by the time squared. Now, this time I'm going to use the equation to its right purpose, and this is the final position. That's what I'm looking for. That is x. What is the initial position? Well, I cleverly chose the origin of the coordinate system to be where the ball is. So the position at the beginning is at the origin. I chose that. I could put 0 wherever I like. So it was kind of smart on my part that I put it where the initial position is. So the initial position is 0. The initial velocity I was told is 20. I just figured out that the time is 2. Negative sign. Why is there a negative sign? Well, because the acceleration is negative 10. You might put your negative sign in the parenthesis here with the 10. It's kind of a style thing. I think that's gauche, so I put the negative sign out here in front and just leave the 10 in there, but that's a negative 10 as that goes. The time is 2, then squared. I chose great numbers for this because 20 times 2 is obviously 40, and 1/2 of 10 is 5, 2 squared is 4, 5 times 4 is 20. So the final position is 40 minus 20 is 20 meters. That means that starting from 0, it goes up to a final position that is 20 meters up. And so I was able to find the position in the future by knowing the acceleration and where it starts. And that's pretty great, especially when you think that this has all happened in just a couple of days. We've advanced to this point where we can start making predictions about position, velocity, and acceleration. It's pretty special. Now that I've worked out the motion on the way up, which was perfectly interesting to me, I'm going to imagine now that I'm up here at the top where the velocity is equal to 0, and I'm going to see what I can work out about the motion on the way down. So on the way down, I need to choose coordinate system again. And so what I'm going to do is I'm going to choose all the way up here to be 0 now. Can I move the origin of my coordinate system? Yes. As long as I don't move it in the middle of a calculation, I'm fine. I finished that first calculation. I've moved on. It's almost like I'm starting a new problem, falling from that high in the air. So I'll choose 0 to be there and upward to be the positive direction, just like this. And I've got this nice icon that tells me my choices. This time I'm going to use my equations in reverse order. Because if I decided here that I wanted to find out what is the velocity when it reaches the bottom, I'd find that that's not going to work out because I need to know the time. The V is equal to V naught plus AT equation really needs you to know the time unless the time is what you're looking for, which can happen. What I'm going to do instead is start with my position equation. X is equal to X naught plus V0T plus 1/2 AT squared. But I don't have to predict what the final position is. I already know. Because I know that the building is 25 meters high, and I know that the projectile, the ball, went up 20 meters. I know what the final position will be. And so for X in my equation, I've written negative 45. Why negative? It's important. You don't want to be the physics student who just plugs numbers in wherever without thinking. Why did I put that as negative 45? The reason is simple. If the ball starts out at 0 here at the top of the motion and upward is the positive direction, when it goes downward, it's going into negative positions. Imagine I had drawn the whole number line vertically. By the time it gets here to the bottom of the building, its position would be negative 45. Position is a vector. It has a magnitude and a direction. This ball is going to go 45 meters in the negative direction. And so I have negative 45 there. I chose the initial position to be equal to 0, aren't I clever? The initial velocity is not 20. That was over here when Slim threw the ball. I'm starting my problem from up here now, new problem, where I'm just dropping the thing from rest with an initial position equal to 0. So the initial position is equal to 0. The initial velocity is also 0. And I have negative 1/2 10t squared. The acceleration is negative again? Yes. That doesn't make any sense because when it falls, it goes faster and faster and faster. Yes. That's why I have to subtract velocity. This is probably the most subtle idea in the whole description. You have to appreciate the thing that when the ball is coming downward, it has a negative velocity. And that negative velocity gets larger and larger and larger. The way you make a negative velocity larger is to subtract meters per second in every second, making it more negative. Shadi, does that mean that the acceleration is negative the whole time? It's negative on the way up and it's negative on the way down? Absolutely. My promise to you is that it is always true. If you choose upward to be the positive direction, then the acceleration will always be negative 9.8 meters per second squared. Here I'm using 10. If I choose upward positive, the gravitational acceleration is always negative. And it's easy math. 1/2 of 10 is 5. The negative signs cancel on each side. If you like to think of it as multiplying both sides by -1, that's fine. Then 45 is equal to 5 times t squared. Quite cleverly, 45 divided by 5 is 9, and the square root of 9 is easy, it's 3. It takes 3 seconds to fall from the highest point all the way down. That means the entire motion takes 5 seconds, because I just add those times together. But it takes 3 seconds to fall from rest. The very next thing I'm going to do is trot out my velocity equation and see if I can work out how fast it's going when it hits the bottom. But I really don't need to do that in this simple circumstance, because if it starts up here and falls for 3 seconds, the velocity is going to be 10 meters per second, 20 meters per second, 30 meters per second downward. So I have to be a bit careful. Let's do it with the equation and see what I get. The final velocity is the initial velocity plus the acceleration times time. The final velocity, which I'm looking for, is the initial velocity, which is 0. The acceleration, which is negative 10 times 3. So indeed, it works out to 30, but it absolutely works out to negative 30. The final velocity is negative. Does that make sense? Yes, because I chose upward is the positive direction, and the object is going downward at 30 meters per second. Velocity is a vector, not just a number, 30 meters per second, but also a direction, negative. Motion under the influence of gravity is motion with a constant acceleration that's equal to 9.8 meters per second squared as the number. And if I choose upward to be the positive direction, which, man, I always will, then when I'm solving problems where gravity is the cause of the acceleration due to gravity will be negative 9.8 meters per second squared.